I'll be talking about eyes-closed safety kernels, safety of autonomous systems under loss of observability. I'm Forrest, Laine, and this is work with Chih-Yuan, Chiu, and Tomlin. We are all from UC Berkeley. Autonomous systems are subject to sensor failure. This can be for a variety of reasons. In any case, we wish that our systems are able to handle these potential losses of observability due to sensor failures or other. In this paper, we present a means for handling these losses of observability in a safe way. To do so, we formalize this problem as an open-loop dynamic Stackelberg game. The framework we present focuses on computing two important outputs. One is a safe operating regime for the system. As long as the autonomous system stays within this regime when sensors are operating correctly, safety can be maintained if observability is lost at any time. The second is an emergency control policy. These are optimal controls to be applied once observability is lost. Solutions that we provide introduce no additional conservatism beyond what is necessitated by the problem that we are modeling. Computation of these outputs are performed by numerically solving Hamilton-Jacobi partial differential equations, as we will show how. The dynamic game that we use to formalize this situation is set up between the internal system, which is typically the ego vehicle, as well as what we denote the external system. This could be an obstacle observed by the internal system. The game starts the moment observability is lost. At that point, it is assumed that the internal system attempts to preserve the safety of the joint system, and the external system attempts to jeopardize it. Due to the external system being unobserved throughout this game, the standard min-max Hamilton-Jacobi Isaacs obstacle avoidance PDE does not apply. To be clear about what we mean by this, let's look at a graphic depiction of the standard observed obstacle avoidance game and see how the game we consider contrasts with that. In the observed setting, we might have the external system take action to move towards the top of the screen in attempting to collide with the internal system. The internal system can sense this action and avoid the external system by moving to the bottom. Therefore, regardless of the external system's actions, the internal system can detect and avoid it. Therefore, this configuration is a winning position for the internal system. In contrast, let's look at the loss of observability obstacle avoidance game. In this situation, the internal system has some kind of observability failure due to a sensor failure or other. Now, the internal system does not know where the external system might have moved towards. Because of this, any potential action that the internal system might take could potentially lead to an obstacle collision. Therefore, although this game configuration was winning the standard observed obstacle avoidance game, the loss of observability obstacle avoidance game, this is a losing configuration. We wish to find the set of all winning configurations for the internal system in this loss of observability setting. This is what we term the eyes-closed safety kernel. Formally, we can denote the game value of this loss of observability game as the following. We denote this game value by vint. And this takes in as inputs the initial configuration of both the internal and external system, as well as the duration of the game. The value is defined to be the supremum over all internal control signals of the infimum of all external control signals of the worst case safety violation throughout the duration of the game. Due to the nested optimization present in this expression, it is not obvious how to evaluate it for a particular initial configuration. While evaluating this value function is very difficult, what we really care about is computing its super zero level set. We show in our paper that this can be computed by solving a sequence of problems with known solution methods. This process is outlined as such. 1. Compute the forward reachable set of the external system by solving a Hamilton-Jacobi partial differential equation. Then, take this set and project or extrude this set into the state space of the internal system, thereby creating a time-varying set of states which the internal system must avoid. Finally, we compute a backwards avoid tube of this time-varying set of states which the internal system must avoid. And this is again done by solving a Hamilton-Jacobi partial differential equation. To understand this better, let's consider the example from earlier. Here, both the external and internal system are represented using simple dynamics models. Here we depict the output of the three stages of the computation outlined 2 slides ago. First, we compute the forward reachable set of the external system. This is depicted on the left. Next, because the internal system does not care about which heading the external system is at collision, we project the set along the heading dimension of the external system. We then convert the set into relative coordinates between the internal and external system and extrude the set back along the relative heading dimension. Finally, we compute the backwards avoid tube of the set, resulting in what we term as the eyes-closed safety kernel. Here, we depict contours of the eyes-closed safety kernel, as well as the forward reach set of the obstacle in 2D space for easy visualization. The result of these computations can be used to maintain safety of the internal system despite potentially losing observability. This can be done using the following procedure. So long as the configuration of the internal and external system stays within the eyes-closed safety kernel, the internal system can be controlled to achieve whatever control goals that system may have. If the joint system gets too close to the border of the eyes-closed safety kernel, or if observations are lost at any time, the internal system should execute the emergency control policy in order to avoid unsafe situations, and until observations are regained and the system is back within the Eyes-Closed Safety Kernel. For more information, please refer to our paper. Thank you. Goodbye.